Well, welcome everybody. It's the December meeting of New Mexicans for Science and Reason. And John Covan, our hardworking vice president, is beating up the bushes to get us a January speaker. But I had so much new material on this flat Earth business that I decided it would be worth an update. I've been doing lots of new scripting, and I have quite a few new computer capabilities that I've brought to bear, and there's just so much flat Earth nonsense out there. They're even invading, as we'll see, innocuous parts of the internet that are not, excuse me, not devoted to the flat Earth controversy. Okay. So any questions before we get rolling? Okay. Well, I'm Dave Thomas. This is December meeting of New Mexicans for Science and Reason, and we're going to get rolling on the topic of what's new in the flat Earth. So let's see here. I'm going to share. All right, there's Randy. Okay. And sharing with sound. Desktop, yeah. Okay. Well, I hope everybody can see that. Wow. Okay. All righty. So I can't see any of the Zoom controls now. That's I'll have to pop out of this if people are needing to get admitted. So here's what I've got. David Attenborough has a wonderful Facebook page, but it was invaded by people that can't believe we have spaceships in outer space that take pictures of the moon from the far side. I've got I call it a simple model for the length of the day, and it is simple as far as the astronomical community and the Navy and all that. But it is actually a very good model to show that our Earth is spherical, because this spherical model with just a few equations predicts how long the days are all over the world. And then there was a amazing voyage around Antarctica in a yacht below the 60th parallel, Guinness World Record event. And the flat earthers are basically, their vision of that is impossible. So we'll show you that. And star trails, what happens when we look at the night sky. I've got some little bit of new material on that. And a quick measuring the radius of the Earth with the Sandias and the internet. I haven't actually been able to do the experiment with people on the ground and on the Sandia crest at the same time. But with the internet, we have a website that says what time sunset is going to happen in Albuquerque. And there's a webcam on top of the crest that can tell you when the sun sets up there. And using those two, I was able to measure the radius of the Earth within 6%. And we'll wrap it up with a look at the sunrise sunset phenomena and the flat Earth explanation of why there is day and night, and how that has some problems with the way things look when the sun comes up in the morning. Just the word, the sun comes up. On the flat Earth, it would be the sun comes in. But we don't talk like that because we've known for a long time the Earth is round. So here is David Attenborough's Facebook page, and just a couple weeks ago, They posted this marvelous picture from the Discover satellite. It's taken live pictures of the Earth all the time. It's 1,000,000 miles out in space, far beyond the moon's orbit. And every once in a while, the moon goes in front of the Earth, and they can get wonderful pictures like you see there. And David Attenborough fans posted that. Well, little did they know that the shit was about to hit the fan. Noah says that's the most fake looking photo I've ever seen. And 100 replies to that. Chris, you can tell it's real because it looks so fake with a sad face. Mark, well, that looks fake as shit. Not saying it's not real, just saying it looks like a construction paper cutout, like a South Park episode. Juan, I thought no one has seen the back of the moon. Well, that's what we have spaceships for. Bert, even if evolution wasn't correct, how would what you said have anything to do with your delusions about satellites? And Alexis answers, the photo, first of all, is illogical to claim satellite imagery exists 1,000,000 miles away. Okay, I've got, there we go. Joe, there we go. And okay, so I can hear when people are popping in. Excellent. So Alexis thinks that today's evolutionary scientists are part of this evil plot to make us think that picture is real. Jorn Hedden actually popped in and said, hey, this is real science. Here's the article about it in Nature from August 2015, one of the best scientific journals in the world. And Paul answers, well, Jorn, you're telling me that you believe everything you see and read? Holy cow. Citations to eminent sources, well-respected sources means nothing. Opinions, everything. That picture looks fakey to me. So it is. Roy, how can they capture a sharp image of Earth from 1,000,000 miles away, but the dude on the news that police need help identifying looks like this? And Chris did point out, hey, Roy, NASA has good cameras, and 7-Eleven has the ones they got on eBay. And there is a difference between cameras. One person on that thread posted this picture with the moon the way we see it in front of Earth. That could never happen. This should be the far side of the moon, if this perspective is to be believed. Like the real picture. There's the real picture. Why is the moon so dark? Because it's really got a low albedo compared to Earth. That kind of looks alien to us because we don't see that side every day, almost every day of the month, like we can the moon. So that when that one came out, I had to react. Rainier said, Animal, no, check out albedo and compare the moon with Earth. Your picture looks photoshopped. The moon is way too bright. But I hopped on there and said, Animal, you posted the near side of the moon that we see from Earth over the far side. This is wrong. The same way this Magritte painting is wrong. And yes, when I have an opportunity to make a point using surrealistic art, I am all there. Okay. So I made this chart a couple of years ago to look at this size issue, because in that picture, the moon actually does look a little too big. So here we've got a diagram shows, here's the Earth, here's moon, and some 384,000 kilometers from the Earth, the 240,000 miles we're all familiar with. Way out here, 1.5 million kilometers away, 1,000,000 miles, is Discover, this cool satellite that got the picture of the moon and the Earth together. And if you look at that picture and digitize it and just look at the pixels for the Earth's and the moon's diameter, Earth is quite about 2.73 times bigger than the moon in that picture. If you look at the moon and the Earth, their actual diameters, the Earth ought to be 3.67 times bigger, little bit bigger. So why does the moon look so large? Why doesn't the moon look almost 4 times smaller than the Earth? And the answer is we're seeing the moon here, but we're comparing it to the Earth there, and that effective diameter is a little bigger. You can calculate how much bigger, and that ratio is exactly the ratio of pixels. The moon scaled over to where the Earth is just under 3 times bigger, just as the photograph shows. So if you didn't know how far the satellite was away, you could use that as an unknown and actually calculate from this picture and the knowledge of the actual Earth and Moon diameters, you could calculate how far Discover is away. So here is that picture again. This is one of the flat Earth memes. If this new NASA photo of Earth and Moon was real, wouldn't the Earth from the moon look more like this? And that shows the Earth from Apollo. I think that's Photoshopped. And not like this, where the Earth looks tiny above that astronaut. Wow. And here's another one. I'll let this sink in. Small Earth from the moon's surface, large Earth from behind the moon. Both photos are from NASA. So this, the flat earthers think this obviously disproves that we have spaceships that can photograph the moon, because the moon should always look the same. No, it shouldn't. So flat earthers say, do your own research. Well, actually, I do my own research, and I thought this is just a simple photographic question. I'm going to set my camera 4 feet away from this golf ball, which is going to be my moon, and that's another foot away from this blue toy ball, which is going to be my Earth. And I picked them because the blue ball there is about 4 times the diameter of the golf ball. So here is that picture from 60 inches away from the location of this camera, zoomed in, and we can see, yes, there's the moon. It's smaller than the Earth. That's what it looks like when the camera's far away. But when I put the camera over here, 12 inches away, right on top of the golf ball, well, of course, the golf ball looks much, much bigger. And that reproduces the shot of the Earth from the moon, where the moon looks bigger. So, yeah, it depends where you are, where your camera is, where the planet and the moon are, as to how big things look. All righty. So I'm going to show you a simple model for the length of the day. And I have latched onto this as really a good argument to defeat flat earthers, because it's actually very simple math. I'm going to show you that. The detailed math, you have to consider the ellipticity of Earth's orbit and minor variations in the axial tilt, and things like the equatorial bulge and whatnot. So yes, that math gets pretty intense. And I've got an algorithm coded up for that. But what I'm going to present today is just as simple as you can get, but it shows that making a few simple assumptions based on a sphere yields you an equation, a pretty simple equation, that tells you how long is day and night here in Socorro in the winter, in New Zealand in their summer, all over, any day of the year, any latitude. It works pretty good. Usually about 10 minutes correct. Sometimes it's as far off as a half hour, but we'll see. The flat earthers are not capable of that. So I've got a little CAD program that I've been learning, FreeCAD, and so I've got a Here's a little picture, a model I've made with the Earth and the sunlight. Here it is looking from the side. So basically, the sun is in the direction of this arrow, and this picture is on the equinox, like March 21st, September 21st, and if we look at it from above, we can see that day begins here. That the Earth is basically turning in a circle, counterclockwise from above. Day begins here, and this edge of the white circle, that's our latitude, say 34 degrees, 35 degrees for Albuquerque. So as the Earth turns, this point moves, and that's daytime. There's noon, and then you get over here, there's nighttime. And on the equinox, March or September 21st, the days and nights are both 12 hours long, and that shows it quite nicely. Now I'm going to close that one and fire up the summer one. And here it is. Let's look at it. Yeah. So in the summer, the sun this is basically a geocentric model where the sun goes up and down during the year. So let's look at it from the side and center that. So we can see here the sun is elevated about 23 degrees, our axial tilt. This top of the sphere, that's our latitude, say 35 degrees latitude. And if we look at it from the top, we can see in the summer, the morning comes a little earlier than it did in the spring, and there's more time as the Earth turns around. It's going to last longer till it gets to sunset over here. Well, that's in the peak of summer, like June 21st. Let's close that one and fire up winter. And here it is. Let's look at it in 3D. And if we look at it from the side, the sun is now 23 degrees below the equator. And if we look at it from above, we can see the daytime is going to begin a little later, and the actual daytime is shorter. Morning comes later, and evening comes quicker. And there you have it. So that's the basic idea. So let's get back into the slideshow. So here is that last one I showed you, the winter solstice, which is just coming up in less than 2 weeks. And so this flat part of the Earth that I showed you, that's a plane of constant latitude, say 41 degrees north. This plane here is the terminator on this side facing the sun. That's daytime. And on the far side of this plane, that's nighttime. And we can see daytime, nighttime. It begins. Oh, and the Earth is spinning at 24 hours. It in one turn there, 15 degrees per hour every day. Here we're looking at the summer solstice, and here's the spring or fall equinox. But let's get back to the winter solstice. If we look at it in the profile, here I've just brought out some equations. This is our latitude. So there's the equator of the Earth, and this point, 41 degrees, that angle, that's our latitude. And that means from any distance from the center to where the inner circle cuts the sphere, that has a radius of what we'd call rho. If we call the radius of the Earth 1, the height is z, which we know is the sine of that latitude, z to 1, sine of theta. So that tells us the value of z depending on latitude, theta. And rho is going to be cosine of the latitude. So the distance from here to here. And declination D is this angle from the equator to where the sun is, which is at our time of year, the sun appears below the equator. Got a negative declination. Here is a super simple formula. This isn't super exact, but if you plug 23.5 degrees times the sine, and then 360 days times the day number. Today is the 347th day of the year. There's websites to look that up. Subtract 80, that turns out to be the spring equinox, March. This formula tells you that on the spring equinox, the sun is at the equator. At the height of summer, it's 23 degrees higher. Fall equinox, back to the equator. And the winter solstice, 23.5 degrees below the equator. So that tells you your declination. So there's two parts to this formula. The second part, here's looking down at the Earth on the winter solstice. And remember, I told you that rho, which was equal to cosine theta, is the distance from the North Pole, at the latitude, like 41 degrees, to where that sunlight's going to hit. And so that is rho, same as cosine theta. And this y, basically the equation for y is it's a constant times z. It's in the yz plane. And so z is sine theta. And that slope of the YZ plane is minus 10 of the declination if that line is positive, if the declination is in winter, and it goes negative for the summer. So you basically realize that this angle, alpha, is just the arc cosine of y over rho, and that's something we have, and we plug in the sine theta, cosine theta, they combine to make a tangent theta. So this angle is a pretty simple argument, and the length of the day is twice that. This angle here, alpha, is the same as there. So you start here, angle alpha there, and so twice alpha divided by 15 degrees per hour is the length of the day. Boom, we're done. So yes, the actual formula, it would go on for pages and pages of complicated corrections for the ellipticity and eccentricity and obliquity and oblateness, and just one thing after another. It is pretty intense. This is the simple one. Two equations, this one right there and that one there. And for anywhere in the world, you can figure out not only how long the day is, but where the sun is coming up that morning or where it sets that evening. So here is today, December 13th in Socorro, New Mexico. And we can see sunrise 7:04, sets 4:59. Length is about 9:55 minutes. And when I plug in to that formula, 34.1 degrees, and the declination of the sun, alpha comes out to about 73 degrees. Length of the day, 9:44, about 10 minutes shorter. And the azimuths, 118, I got 107, so that's about 10 degrees off. 242 there, I got 253, about 10 degrees off. Here is on the other side of the world, down under, and this is New Zealand, Christchurch, New Zealand. They're in their height of summer. Their summer solstice is coming up, and sun comes up 5:42, sets 9:04 p.m. Great summer day. They're at minus 43.5 degrees, 43 degrees south. Their length of day is 15 hours, 22 minutes. And my little formula says 15 hours, 13 minutes. So these are vastly different. This is 6 hours about shorter than that one. But yet this very simple sphere-based, geometry-based, science-based model actually predicts the azimuth and location of the where the sun rises, how long it's going to take. And I think that's a great thing. Why do I think it's a great thing? Let's go back to the equinox. On the equinox, March or September 21st, the sun is like above the equator. It's way over here. It's 93 million miles away, but it's above the equator. And everybody on Earth has a 12-hour day and a 12-hour night, because the Earth, we're showing the poles, North Pole, South Pole, the Earth is turning. And so we can see, yeah, I think this is for Greenwich Mean Time. There's London, there's Greenwich, and yeah, parts of Spain and parts of Africa, they all experience sunrise at exactly the same instant. The sun is due east. Everybody is looking east at this rising sun, and then west at the setting sun. Here is what we've got with the flat Earth. Basically, they say the sun goes around the Earth. It's 3,000 miles up, and it's kind of like a spotlight that shines out. And so here is the situation on the equinox, except I've plotted it on what's called the flat Earth map, which is just a polar azimuthal map that doesn't do too bad for the northern hemisphere. It extremely exaggerates. I mean, look how stretched out Australia got. It's not a very realistic representation. The South Pole is this entire circumference of, if you've ever seen that picture of the barber's pole at the South Pole, that goes the whole way around this map. The South Pole is the complete outer rim of this map. So it's not very realistic. Well, anyway, here we've got the sun, and it somehow knows, the sun seems to, we'll consider it. If the sunlight can reach Antarctica over here and over here, then why, in the course of this very day, doesn't the sun light up North America and South America too, for that matter? And that's because it's impossible to come up with a simple model. Some globe-minded person said, hey, just putting this out there for the flat earthers, day and night with the globe, day with the flat earth. And the flat earthers responded and said, well, the flashlight just lights up part of the flat earth, and the other part's night, day and night. That wasn't so hard. And that's actually their argument. Yeah, the official, even all the way up to Eric Dubay, this is one of the memes he puts in his movies. If the earth is flat, why don't we see the sunlight 24 hours a day? The same reason why this light bulb can't illuminate the entire wall. The light is small and localized. And they really say this, that the light from the flashlight peters out. It gets dark once you get far enough away. But if you're over here like a mouse on the edge of the room, you can see that bulb. It's on. If you're in a movie theater and you look back at the projector, you can see it even if you're in the dark. It's just a wacky concept. So think about that when what stops the sunlight here and then allows the sunlight to get to New Zealand. New Zealand is farther from the sun. It's right over the equator than New York City. Wow. So why is New Zealand lit up and New York City not? That's some hard math. I mean, try to come up. I mean, I came up with this simple equation that tells you day and night and length of day on the round Earth. Two equations, not so bad. But imagine Einstein himself could not come up with, okay, because this is just one day, the equinox. It gets worse. It gets a whole lot worse. Um, so actually, in the summer, on June 21st, our summer solstice up here in the north, on this crazy polar map, it actually works pretty well. Here's the sun that's over the Tropic of Cancer, and it actually does look like the path of a sort of spotlight beam, like that in the meme we just saw. But that's the summer, and we saw how bad the equinox was. And when you get to our winter, summer in the southern hemisphere, you've got this big dark zone of night that's exactly the analog of the lit up portion in the summer, and you've got daylight. Somehow the sun knows not to shine here, but to actually shine all the way across to light up Antarctica and make the 24-hour sun in Antarctica in the December months. Wow. So that would Einstein himself would not be able to. I've tried to come up with the math, and the only way that I've made these charts is to just look at the reality of the situation, go back to that picture of the globe Earth with half of it lit up, and say that's the part that's lit up, and now let's plot that on whatever wacky map projection you want to, and that's how I get these things. That's why these there are better graphics renditions of all these things, but I've got my own flat Earth model that it's useful to be able to code that up and talk about it. This is what's called the Gleason map, the official map of the flat Earth community. But the guy that published it in 1892, I think, even though his patent said, "Oh yeah, this is a projection of the globe Earth," in his heart, he knew the Earth was flat. He knew this was the real map, and he wrote a flat Earth book. Is the Earth a globe? So that is Gleason. Here's my rendition of the flat Earth map showing seasons. We've got the sun magically flying 3,000 miles up in the air and going clockwise like that. And the solstice, the sun is 6,000 miles from the North Pole. And then it magically knows for the summer, to shorten that orbit to 4,400 miles. And then in the winter, extends it to over 7,500 miles. And supposedly that's why we have our seasons. So this is where I used to work at Quasar in Albuquerque. We had a nice hallway that was due east west. Somebody went to a lot of effort to make that hallway exactly east and west, and on the equinox on March or September 21st, I would always stay for sunset, because on that one, it was like an Indiana Jones thing. It's like Stonehenge. On that day, the sun flooded and filled up that whole hallway with light. So yeah, everywhere on the earth, the sun sets exactly west on the equinox, and it rises in the east. Everywhere on the earth, even in New Zealand. So I found this movie that has the flat Earth explanation. You are going to be thrilled with this. Here we go. Sunsets and equinoxes illustrated on the flat Earth model. And here we're oh shoot, that's just recent. What I need is okay. I'm having okay, let me go to QuickTime. Okay. Oh, I'm sorry. Okay. Zoom really makes it hard to see where a lot of things are. Okay, here we go. And okay. And we've got this movie, Sunsets and Equinoxes. Here we go. And let me begin and start this. Here we go. Wow, that's some movie. Okay. Wow. Okay. Um, all righty. So yeah, that's just mind-gobbling. Um, basically, yeah, well, the light rays just magically curve around so that they all come in from the west or the east. Yeah, and why does that happen? No answer. That's a great example of cargo cult science. They are, I mean, that's some advanced graphics and animation, and they're using the movie computer generated imagery. And boy, is it pseudoscience. It is the modern day cargo cult. So here's a new topic. These brave people circumnavigated Antarctica. It took about 100 days. They went over 15,000 miles in extremely harsh conditions. Wow, quite a trip. And there's a movie about it. This shows the from their website. They started from Cape Town in Africa, and then once they got to Antarctica, they kept under the 60th parallel, came all the way around. Here's South America, Cape Horn, and continued around Antarctica. And then once they got to their crossing point, had made a good tight crossing around Antarctica. Then they headed up to Tasmania and in Australia. So pretty impressive voyage. There's a website. There's a Guinness World Record for them for achieving this. And here is my rendition using my globe map over the weekend. I added the capability to read in any set of coordinates, like the coordinates of their journey, and plot that on a view of the Earth. This is the Earth viewed from the South Pole. So we can see South America and Little Africa and Australia, Tasmania, New Zealand. And this shows they left from Cape Town, went around, and on their journey, Antarctica was on the starboard side, and South America would be on the port side. Now this is what this would look like on that crazy Gleason map, or the accepted flat Earth map. North Pole is at the center, and they start at Cape Town, and then they go around, and they pass by Australia on the left, on the port side, and Antarctica on the starboard side. They continue around, and remember, the circumference of this map is 75,000 miles long. The circumference of this map is 3 times the actual circumference of the spherical Earth. So this is quite a trip they're racking up. In fact, it comes out to, I think, 83,000 miles. You can see where they end up in southern Australia, Tasmania. So here's the flat Earth answer. They cheated. Now, this is for a different yacht race, but they did go around Antarctica, and they did start from kind of around Africa and make the circle, and they didn't quite loop around like the Polish team did. But just look at this carefully. Here they're going Australia on the left, Antarctica on the right. South America on the left, Antarctica on the right. That's the real voyage. What the flat earthers say is, oh no, they just came down from France around Africa, and then once they got to the Cape Town, they just went, and they saw a little bit of ice, and then they went up to South America and came right up, and that's how they went. No, look at Australia over here. They need to go in between Antarctica and Australia, and this map doesn't show that. So I fixed it for them, and I actually posted this where this meme was originally published. They did not approve my post because I guess it didn't meet their community standards. But here's the actual path, which would be, again, about 75,000 miles. And you'll notice, yes, they're passing Australia on the left, Antarctica on the right, coming up from behind South America, and proceed back to France. So that is, of course, that's not reality. It didn't really take that long. But if you actually had that flat Earth map, that's the kind of voyage we'd be talking about, which would take years. If the team could do 15,000 miles in 100 days, then it would take years to go the 87,000 miles on the flat Earth map. So there's a great movie they actually made. There's a YouTube. You can find it. Just search for Around the Ice. And it's the official video of this incredible voyage. I mean, these guys put up with some hard conditions. Here, they went around Antarctica on the right, Cape Horn on the left, and in this video, it's in Polish, but it's if you turn on the captions, you'll learn, oh yeah, we passed famous Cape Horn on our port side, and we saw ice-capped mountains of Antarctic Peninsula. The flat earthers say the Antarctic is just an ice wall. There's just a wall. You can't even get onto Antarctica. It's just this impassable wall, and that there's helicopters that'll shoot you down if you try to go. No, here's the yacht, and they're to the starboard side. Those mountains, that's Antarctica right there. That's not an ice wall. Yes, there are ice walls, but they don't go around the whole of Antarctica. Ice shelves, not ice walls. So here is in relation to this discussion about Antarctica, somebody got Google and tried to find the distance from around the 60th parallel to the geographic South Pole. And they tried all these distances. I don't know how they were using Google, but even though these are all on 60 degrees south latitude, and it really shouldn't matter what the longitude is, you're going to the South Pole but somehow they managed to get different lengths. I don't know how they were picking the South Pole, but 1,800 miles there, 2,400 there, kind of some discrepancy. Here's the worst discrepancy, about 700 miles. And so I've actually, here is the simple math. It's just a pretty simple equation to determine geodesic distance between any two latitudes and longitudes on the Earth. And when I crunch that for 60 latitude 145 to the South Pole -90, doesn't matter what the longitude is. I put in 0, but any longitude would give you the same answer, just under 2,075 miles. So that one is too small. That one's much too small. I don't know how he got these, but he basically, here's somebody on the internet that says, I'm using Google, that's high tech, and because I'm getting inconsistent answers, that means the Earth is flat. No, it doesn't. That's making mountains out of molehills. Okay, so I went ahead and on the flat Earth map said, okay, let's look at 60 south and 30 west to the South Pole, and let's look at 145 west. That's way up here. 145 east, rather. Oh, that's a mistake. That should be 145 east, but west would be over here. Same distance, and it's 6,000 miles that way. Remember, it's just about 2,000 miles on the real world from 60th south to the South Pole. On this version of the flat Earth map, 21,000 miles. Holy cow, that's like more than 10 times the actual length. So the complainer, yeah, here's that geodesic formula, pretty simple formula. He was complaining about, maybe 10 or 20% error. He's got errors of 10,000% using the flat Earth map. And for the curious, there's the simple Earth math and the kind of simple flat Earth math. Basically, this is based on if you use the Gleason map, this will give you the right radius as a function of latitude, and you can describe any point as a function of longitude, x and y. You can calculate the distance between them, and that's how I did all these calculations. So where he was complaining 2428, it's not the same as 1734. Yeah, and they're both wrong. They should have been 2075. And if you actually do it on a flat Earth, 21,000 miles, 10 times too long, or 6,000 miles, about 3 times too long. So math kills flat Earth. Here's a nice map of Australia. If you take that Gleason map and sort of twist it around to get Australia right side up for us north centrics, look how stretched out and wrong. It's wrong. So I used my little geodesic formula, calculate, hey, let's look at Albuquerque to San Francisco. And if you look up flight times, this is the distance you'll get as the bird flies or as the plane flies. The flat Earth calculation in the northern hemisphere, it's maybe 10% too big. It's kind of 100 miles too big on around 900. Now, if we look at Sydney to Adelaide down here, down under, geodesic, it's actually 150 miles less than Albuquerque to San Fran. But the flat Earth distance, because the southern hemisphere is so exaggerated on this Gleason map, flat Earth distance is 1,800 miles, 2.5 times bigger than it should be. So where it was, maybe 10, 12% off here, it's off by many times. Many hundreds of percent here. Wow. Speaking of Australia, some flat earthers actually say there is no Australia. They say, well, look at the animals like the platypus. That's obviously a make-believe animal. God wouldn't make that. It's all a dream. So this map shows it has New Zealand, but no Australia. Wow. Speaking of Australia, here's a flat earth meme. It doesn't take much fuel to launch a rocket. When you launch from Australia, you just untie the rocket, it falls into outer space, and it's then guided by its engines. And you might laugh, but that is the flat earth concept. That's what they say. Up, north is up, south is down. And this is one of their memes. Free balloon rides in Sydney. If you believe in that globe earth, ha ha ha. This is actually what they believe. North is up, south is down. When actually we all know that up is up, and down toward the center of the earth, that's down. All over the world, in Australia as well as New York City. And so this is a honest to God flat earth meme. If gravity is not strong enough to stop a small stream from flowing to its lowest point, what is stopping the oceans north of the equator from emptying into oceans south of the equator? This is what the earth would look like if we lived on a globe. Gravity is pseudoscience, a theory that can't be proven. Holy cow. This is wrong. Very wrong. How wrong? I've got like 5 levels here, and they're all labeled wrong because this is wrong on so many levels. Had to do that. Sorry. So that brings us to star trails, entirely different topic. And basically, this is a real picture from Utah with a long exposure. And you can see the stars were curling counterclockwise above around Polaris. They're going counterclockwise in the southern hemisphere, but of course we can't see the southern pole because this big planet Earth gets in the way. But this pattern is a spherical Earth pattern, what we'd expect. But the flat earthers actually say, oh no, you can't explain that with a globe Earth. Only the flat Earth explains opposing star circles. Wow. So being a physics-minded computer programmer, I wrote my own simulation to make videos of what the stars look like if the world was flat or if it was round. And so I got 3 models for you here. On the left, I've got the globe Earth star sphere. So, and this basically, of course, the stars are, some are close, some are far, but here we're all projecting them on this sphere. Astronomers do it all the time. The right ascension and declination of any star on this sphere can tell you where to look for it from our earthly perspective. So, so we see there's the Big Dipper up there in the north, and there's Orion. It's kind of on the equator, and then on the southern hemisphere, I've got the Southern Cross, and it'll make an appearance. There it is, Southern Cross. It's hard to see because it's down south, but basically I've just limited to these 3 constellations plus the pole star, Polaris, just because it gets kind of confusing with 300 stars. Now in the middle, I've got the flat Earth with a star sphere, and some flat earthers say, well, of course the Earth is flat, but the stars are in a sphere, much like the one that I described on the left. So for this, I've got a disk, a flat Earth, but a star sphere, and there's the Big Dipper in the north, and here comes Orion around the equator, and there goes the Southern Cross down south. For this last option, I have made a flat star disk, and in this, where do the stars go? Well, in the southern hemisphere, when you're down here at like near the South Pole, you're looking straight up to see the Southern Cross. So Southern Cross has to be above the outer rim. The Polaris has to be above the North Pole. Big Dipper has to be above the northern hemisphere. Orion has to be above the flat Earth equator. And there we have it. There's our three options: globe, flat Earth with a sphere, and flat Earth with a star disk. So here is a animation I made with Python. On top, I've got, and this is for 45 degrees north. And here's Orion, that's arising. And there's Sirius, I've included just because it's such a great little marker. And we can see the Big Dipper is indeed going counterclockwise around Polaris. But Orion actually rises. It rises in the east, gets high as it can in the south, and then sets in the west. And it does this every night. We just can't see it in the summer because the sun is in the way. But right now in the winter, beautiful time to see Orion. What's this down here? That's the Southern Cross. This brown is below the ground. Basically, if we had X-ray vision, then we could see the Southern Cross through the ground. But basically, this is reality. Orion rises and it comes up above the horizon, peaks in the south, sets in the west. Now, the flat Earth star sphere on the bottom, you'll notice that the Big Dipper, Orion, just always goes around the equator. It never rises. We can't see the bottom of Orion ever. And the Big Dipper doesn't go around Polaris, which we can obviously see it go around, but no, this Big Dipper just kind of moves across the sky from left to right, kind of curling down here and then up there. This is wrong. This is not what we see at all. From anywhere where 35 degrees north is kind of close to 45 degrees north. So let's go to star disk. And this, so it's exactly the same thing on the top. Just I have that for comparison on the bottom. Now with the star disk, now at least the Big Dipper looks like it's going counterclockwise around the Polaris. And Orion, it's up. It never rises above the horizon. It's always in the sky. And so is the Southern Cross. According to these guys from places like New York City, you should be able to see the Southern Cross. It'll be right under Orion there and the Big Dipper. Holy cow, that's impossible. That's not what it looks like for us at all. Orion comes up and then it sets. It doesn't stay in the sky the whole night.
Hey, Dave?
Yes, question.
What is the latitude at which you no longer can see the Southern Cross
So I
going
think
north?
Albuquerque, you can see a star of it. So, but you don't see the whole thing.
Okay.
But
So you have to go how far south?
we can see a star of the Southern Cross, but you have
No, I
to
understand that.
know what it is, where to look. Yeah.
You can't tell it's the Southern Cross because you can't see the rest
You
of the
can only
cross.
see the one star of it. Yeah.
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 But how
I
far
think,
south do you have to go?
from a few degrees north of
What's that?
the equator, you can see it.
I'm sorry. I didn't.
Question. Okay, so here I've got southern hemisphere and globe Earth star sphere on the top here, and now you'll notice Big Dipper. That's below the ground. We don't see the Big Dipper. We do see the Southern Cross, and it's circulating the southern pole clockwise. And here comes Orion, and it rises in the east, and it's upside down. Sirius is on top, and Orion is totally upside down and peaks in the north and sets in the west. And this is actually what my friends in New Zealand and Australia see. Now on the bottom, I've got the star sphere. So again, Orion never rises above the horizon. It just, you can see the top part of Orion, but not the bottom. Look at the Big Dipper. you can see the Big Dipper. Okay. Okay, I think that was yeah, so this is very confusing. Um, what you can't see here is the Southern Cross, because the Southern Cross is underneath the disk of the flat Earth. So the star sphere just doesn't work. It's not even near close enough to explain uh, anything with the flat Earth. So here's the star disk where the stars are above. Same thing on the top for the globe, the same upside down Orion. But here we've got um, Orion is going counterclockwise around the Big Dipper. You can see the Big Dipper and Orion going around Polaris. And here comes the Southern Cross, but instead of going around Polaris, it's going to continue, and then it's going to go around the southern pole. Wow. So, and that's not what happens. We don't see Orion all night. In Australia, they certainly don't see anything like this. They do see this. So here's one I made with the actual top 300 stars. This is for Socorro's latitude. And I made this because it really compares pretty nice to this picture from Utah that shows a very similar phenomenon. That the southern pole is below our line of vision. It's blocked by the Earth, but the Polaris is up there, and yeah, makes me want to try star trails. This is a picture my friend Tom Dillon took just a few weeks ago. He was on a cruise, and he went to the null point at 000 latitude, 0 longitude, directly south of Greenwich, just off Africa and the Atlantic Ocean there. The null point. They have a party there. People cross there and they break out the champagne. And here is Orion, which we can see pretty sideways there. He was 7 degrees. This picture was 7 degrees south of the equator. And there's my simulation of what Orion should look like at that time from that latitude. So pretty good match. And here, our last speaker from last month, Carl Reinecke, made a bang up movie of Orion, which we can pop over. And I think it's over here. Reinecke, right here. This is a time lapse he made. We don't get to see all of Orion, but a little bit. Kind of pops up at the end. There's the sword. There's the belt. Bam. I love the meteors. Okay. Okay, so there I've sort of drawn out Orion as we saw it at the end of the video. Here it is in the simulation from Placitas latitude. So yeah, pretty good match. So this next to last topic is finding the radius of the Earth using our wonderful Sandia Mountains and their watermelon colored sunsets. Yeah, you can use that to find diameter of the Earth. And several locations of Albuquerque are noted. Like here's Alameda, 5,000 feet. Albuquerque is about a mile below Sandia Crest. So the plan is to have somebody in Albuquerque, and when the sun sets, they start a timer, and they're communicating with a team on Sandia Crest, and so they run their timer, and when the sunset finally comes to Sandia Crest, then they measure that time. And this is a pretty well-known way, like in the Burj Khalifa building in Qatar, I believe, is so tall that you can see sunset from the ground, hop in that elevator, get to the top floor, and see the sunset again. And you can use the time difference and the height difference to calculate radius of the Earth. How do you do that? Well, actually, here's how. The angle that the Earth rotates. So here's the Albuquerque at sunset, and the Sandia Mountains are sticking up there a mile. They're in full sunlight, but Albuquerque is just having sunset. And this shows maybe 5 minutes later, the Earth has turned this angle theta, and this brings the Sandia Mountains to where the top of the Sandias are just now having their sunset. And so it takes time for that to happen. Sunset at 5,000 feet versus sunset at 10,600. So there's your H of about a mile. And so that if it's 5 minutes, you just multiply the time by 2 pi, divide by the number of seconds. And then, of course, time has to be like 300 seconds. And then you get this angle. It's a really tiny angle. And then here's the math from this. The exact equation is right there, but there's some neat approximations that make for this much simpler formula. Diameter is 4 times the height divided by the square of that angle that you found in radians. And the reason it works is because this angle is a really small angle, and we have some neat small angle approximations. But basically, yeah, 4 times the mile divided by that angle squared. So here's Anthony, who tweeted, we have a saying in Albuquerque, when the mountain turns pink, it's time to drink. That's the magical time I'm talking about, the wonderful Sandias time. So just time it and you'll be measuring the size of the Earth. So I did a cheap version of this. I'd like to do it in person someday, but and I'll have to have help to do that. But meantime, I just went to timeanddate.com and said, yeah, tell me when the sun sets in Albuquerque. And then there's a webcam on the tram. And here it is at the time of sunset. And they have these, basically, it's not a continuous webcam. They post a new picture every minute. So you have to kind of be on top of it and save an image every minute to get a log. But I was doing that this afternoon. And at the time of sunset, sun was shining on the tram. That's sunlight there. But some 5 minutes later, that sun finally disappeared. This sunny spot here, it hung in until this frame, that patch disappeared. And so 5 minutes, it took 5 minutes for the sun to set, and angle theta 0.0218 radians, and 4h over the square of that. The diameter of the Earth, 8,000, a little over 8,000 miles, and it's actually slightly under 8,000 miles. So about a 6% error, not bad for the internet. And that brings me to my final topic, sunrise and sunset. And yes, I'm going back to this meme because this doesn't work. Just like you can see the projector in a movie theater, this does not explain day and night. The light is not small and localized. So let's see how sunrise plays out with this approach. So I've made some animations. This is something I've just finished. Been wanting to do it for a long time, but just finished it in the last couple weeks. And the tricky point was getting these shapes like mountains and clouds to light up, to have part of them light up as the sun hits them. But I got that working. So here we go. Sunrise on a flat Earth on the left, where basically we have the sun is approaching from the left to the right, and as it gets closer, it gets light. Whereas on the right here, we're going to have the sun coming from behind a globe, and as the Earth turns into the sun, basically the sunlight comes and it's going to hit this cloud first, then the mountain, then the tree, and then the house. It's going to be the exact opposite order of the flat Earth, where it's first the house, the tree, the mountain, and the cloud. So here we go. Animations compared. Flat Earth on the left, and watch this cloud over here. It's the cloud that gets hit first with the sunlight. It turns pink. Then the mountain top turns pink. Bottom of the mountain still dark. Finally, things like trees, and finally the house, the closest thing to the oncoming sun, get lit up. Finally, over on the flatland, we're lighting things up in the opposite order. In the opposite order. So this is a pretty strong test of flat Earth. Over here on the sphere Earth, cloud lights up first, then the mountain, then the tree, then the house. But on the flat land, it's first the house. There it comes. And there we go. There's the house. Now the tree. Now the mountain, and the clouds light up, and it's morning finally. Wow. So there's my little animation. So I did the experiment. So here is the just a couple blocks where March 12th, 2022. Here it is at 6:17 in the morning. The sun had not risen. Looking east, there's no sun. Looking west, the mountains and everything are still not lit up. It's sun has not risen. Some 15 minutes later, looking to the east with my filter on my camera, yes, the sun was rising. And looking to the west, everything was lit up by wonderful golden hued sunlight. So here is the video for that. Actually have a couple videos, Mount Rainier and Mount Fuji. So here we go, Socorro. Here we go. So this is about 1 second per minute. And there's that beautiful shadow of the Earth coming down, mountains all lit up. Now the church and the tree light up. And given this, I can take this back, and so right, yeah, right there, the tree is just starting to light up, but it still hasn't lit up that traffic sign. So the tree gets a hit first before the closest thing to the rising sun. So there you have it. There's the shadow of the Earth. All righty. And let's, what have I done? I went to the wrong thing here. Let's go to Mount Rainier. So this doesn't happen just in Socorro, New Mexico. This happens all over the world. Everywhere there's beautiful mountains and sunrises, just beautiful. And bam, there you have it. Yeah, that's all for that one. And I have Mount Fuji. Fuji, here we are. Huh. So you can see the sun is at the camera's back, the filmer's back. And so he's looking west. Sun's at his back from the east. And finally, the close area is finally getting lit up. Excellent. Okay. All right. And we'll close that one. Oh, got all these videos open. Yeah. Okay. Great. Uh-huh. Okay. So that is our conclusion. Hope you enjoyed those topics. There's tons of other experiments I've done. I've talked about some of them before, so really wanted to talk about the new ones mostly here. The star trails I think I may have presented here and there, but it's a pretty good one. Anyway, most everything else is kind of new stuff, and I appreciate comments on, do you think the math approach is worth putting out there? I really like the idea of challenging the flat earthers. Okay, show us your math to explain things like how long the day is or where the sun comes up. But in closing, if the earth was flat, cats would have pushed everything off by now. The only thing flat earthers have to fear is fear itself. All righty. So that's good. I can stop sharing for now. All righty. Hope you enjoyed that. Uh-oh.
Very nice job there, Dave. Very
Excellent.
good one. Yeah.
Well, we'll have it on the YouTube. Looks like Jerry's on the phone. Okay. Any questions, comments?
Yeah, Dave, I have one.
Yeah, hey, Marilyn.
Can you hear me? I used to work downtown many years ago in a high-rise building that had windows on the east side facing the mountains. And at sunset, you could see the sun hit the downtown area, sweep up the northeast heights, go up to the mountains and above you, and then beyond you, because we couldn't see west. It's like it formed kind of a backward C, starting downtown and going all the way up. And it was just so impressive.
Oh, yeah, I bet
Yeah,
that'd be
I-
a great thing to get a time-lapse video of.
Oh, that was way back in the 60s and 70s. I didn't have the technology for that. At least I
Yeah.
didn't
Oh, yeah.
anyway. But it was really impressive to see that.
Yeah. Oh, it sounds wonderful.
Yeah.
Okay. Yeah, any other comments or questions? So Skeptical Inquirer wants an article about all this, so I have to start cranking out some thoughts.
Dave,
Yes.
it seems like this is just a continuous game of whack-a-mole because wherever you push and show something, they're just going to obfuscate and come
Yeah.
up with a different explanation. Your Mount Fuji video, well, weren't you just lying? You were actually looking the other direction. You were looking east instead of west. And so the proof of which direction is east and west depends on a person being there. And how can you convince them when they don't want to be convinced?
Yeah. Well, I think that Edinburgh example, I mean, that's a place where, you know, it's not really even the flat earth community's little echo chamber, but I think that shows that you do need people to try to inject you know, a little bit of rationality and
What is that you're referring to?
You know, huh?
What is it you're referring to?
So when I started off, I showed you how that picture of the not the dark side, the far side of the moon, taken by Discover satellite.
Oh, that one. Okay. Yes.
Unusual picture, but David Attenborough fan page put it on their Facebook, and many people said, "Oh, that's fake. I just think that's fake. That's CGI." But there were, sensible people that said, "Hey, this is explanation. This is explained. The moon looked dark because the far side has a low albedo, and it doesn't have the same geology that we're used to on the front side. But it was published in Science and Nature and whatnot. So I think if the people that can combat this irrationality decide to fold their arms and say it's beneath me, I'm not going to waste my time on that, then that does society a disservice, because the people that are just out there having fun, maybe they haven't had time to watch that documentary on the solar system, but
Well, your visualizations are so simple and neat that they maybe have a chance of catching somebody's short-term interest.
What I'm gonna do is there are many popular YouTube video makers that of course there's a ton of flat earth videos, but there are people like Simon Dan and Dave McKeon and Bob the Science Guy from Minnesota, who are making detailed videos where basically, and this is kind of what I'm planning to do, instead of a long talk like tonight's, I'd have like a 10-minute video on sunsets, and I'll say, well, here's the sunset. In fact, I've already put one on our NMSR YouTube page, but I need to add, and I'm learning how to add things like overlays, like me talking underneath a video of the sunset. So, but basically, if you can get stuff on YouTube and TikTok, then when people say these wacky things, you can say, "Oh yeah, here's a 5-minute video that explains why you're wrong," and other people will benefit from that, and they'll go, "Wow,
yeah.
that guy was wrong, and that video was really neat." And so that's my goal, is to increase doing that.
Great. Thank you.
Okay, I got my official Round Earth t-shirt on today. Okay, well, so yeah, John Covan has some interesting a speaker we've been after for a long time. I think she finally might be able to talk to us, so that should be fun. But in the meantime, take care out there, and keep looking up. There's a great meteor shower tonight and tomorrow night, and for actually a week or so. The Geminids are peaking, so check that out. Okay. Right.
Hey,
Well, goodbye, everyone.
Dave,
Yeah.
question.
Oh, yeah. What you got?
Yeah, we got a question. Do they believe, the flat earthers, do they believe that the earth is flat, like Euclidean flat, or maybe it's domed a little bit like a cake that rises in the center, and so it would be a little bit more Riemannian, like calculations for instead of Euclidean calculation.
So I have seen concave Earth. Yeah, but the convex, I'm not sure I've seen that. Let me take a quick oh, here it is. Okay, let me oh darn it, here we go. Let me get back to Zoom, and I found it. Okay, share screen. And can you see it?
Yeah.
So yeah, it's the square and stationary Earth. This is from Professor Orlando Ferguson. Hot springs. Oh, let's see. How can I? Yeah. Yeah, here we go. 1893.
Oh,
Yeah. And there you have it. Yeah, it's the North Pole. Very similar to the Gleason map, except it's got this big basin for the equator. And wow. You'd think, and there's the ice wall around the rim. Yeah. Yeah. Yeah, that's one of the things that the flat earthers, they just don't realize when they put the South Pole, which is this nice area which has a little barbershop pole to mark it. When they make that the rim of the earth, that really screws things up. It's pretty amazing. Yeah. Okay. Well, that was successful. Let's see if I can go to okay. Here it is. Let's try convex. You can see sort of various convex Earths. Here we go. The documentary. So apparently,
If I told you that there was
no.
a tried and true method that would help you land a TEDx talk in the next 30
Throughout history, various civilizations have questioned the shape of our planet, creating hypotheses according to their level of knowledge. Even today, scientists around the world question the truthfulness of the sphericity of the Earth, because even though it's presented as a truth, there is no unquestionable scientific evidence in this regard. Everything on which science bases itself are only evidences. And evidences are not proofs. In order to bring the light of knowledge on the true shape of the Earth, researchers of Dakila and Ziggurat's Technology Center joined with other scientists in an independent research that lasted 7 years, seeking scientific and definitive proof to demonstrate that Earth is indeed round or has another shape.
oh my God, an hour. Let's get to the end.
But on this trip we did here on the Tre Mare Dam, we did a very important test. That is the projection of a laser at a distance of approximately 18 kilometers. And it is known in cartography and by the conception of the sphericity of the Earth that we cannot see a thing beyond 10 kilometers. So we witnessed this experience with all success. It was done at night.
Laser games. Okay. I remember these guys. Wow.
Virtual
Yeah, I remember. It's sort of a flat Earth that was a couple of ponds that were separated. See if I can find it here. They got a ton of badly done experiments.
There-
Just amazing. Oh yeah, this guy's famous. So I think they were some of them. Oh, here we go. Here we go. Yeah.
The magnetic field is also responsible for modeling the shape of our atmosphere, which takes the form of a plane convex lens. In this way, the atmosphere, formed by several gases and water in gaseous state, takes on the characteristic of a gigantic magnifying glass with a high degree of refraction, responsible for day and night.
Oh yeah.
The following experiment simulates the behavior of day and night. We use a flat convex lens, a model of the continents, and an external light source simulating the sun. The result is a model of day and night in the corresponding time zones.
What helped us a lot in this research was the information we collected at our own astronomical observatory of the Ziggurat's
Wow.
Technology Center.
That's wild stuff.
In this manner, the researchers concluded that the Earth is neither spherical nor geoid, but rather convex on the continents and flat in the waters. In this concept, the Earth is like a huge, misshapen asteroid floating in space, surrounded by a very high layer of ice all along its edge. And how do satellites work in the convex Earth?
Okay.
The magnetic field of our planet is primarily responsible for keeping the satellites in orbit.
The magnetism.
Briefly, there are two types of satellites, the geostationary and the orbitals. The geostationary ones are apparently fixed in a position over the surface of the planet. I say apparently because its orbit has to be corrected periodically. Orbital satellites are in orbit over the surface of the planet. They have different routes and altitudes according to each application.
Well, that's pretty wild. Okay. Convex Earth. See? You just never know. Well, thanks, Bill. That was fascinating. Okay.
How do they account for the difference in gravity on the Earth? Because they are believing that it is an acceleration of the whole Earth.
Just today, I had a flat earther tell me it's just electrostatic force. Electricity is much stronger than gravity, and gravity doesn't do anything, and it's electrostatics. Yeah, it's appalling how bad science education is. But yeah, like I was saying earlier, if people do engage the public on YouTube and TikTok, that'll be a good thing, because people don't like to get lied to, and they don't like to get fooled, and if we can spread that knowledge, that'll be a good thing.
Is it the Cavendish balance thing that was used
to measure gravity? Yeah.
And how do they account for that?
They say it was a fake experiment, that nobody ever did it, and physicists say, hey, it cost a couple $1,000, but you can buy a kit to do Cavendish for your college or university, and they do it all the time. And of course that just goes off like water off a duck. Yeah, my dad, way back when, described the creationists as the ducks at the carnival or the state fair. They just pop up, you shoot them down, and they'll just keep popping up. But it is important to keep popping those balloons of pseudoscience just for the sake of the general public. And it's kind of interesting. I've I like writing programs. That was really cool, writing a script to capture having some light beam hitting an arbitrary polygon and carving the part of that polygon that's lit and making that a different color. That took a couple days of interesting programming. Okay. Well, in case unless anybody has any more questions, we'll let you go. That was fun. I think I had no idea I'd be learning about convex Earth tonight. That was great. So we'll see you next time. Thanks, Bill. Live long and prosper. All righty.
Good
Take
night.
care. Thanks, Marilyn.